Recording is on.
Hello everyone, and thank you for joining our call today. Today we're gonna have a presentation, and Maxim, if you're ready, when you're ready, just feel free to start, share your screen, and let's get rolling.
Well, I'm practically ready. So I will start the screen sharing then. Just trying to find that button here. Not really convenient. Shall I start?
Yes, feel free to.
Yeah. So today I would like to start with sharing some brief on the development updates that happened over the last weeks. And because these development updates are very tightly related to customization of RGB smart contracts, I will use this opportunity to share more information about how RGB client-side validation works today, how it is planned to work with what we call RGB version 1, which is basically a standard implementation of complete RGB functionality, which can't be changed since that point, because with the client-side validation, we don't have soft forks or hard forks. It's just done that way and forever. And maybe many years later, we will have RGB version 2, which will be just a different protocol, in fact, and not compatible at the bytecode level with RGB version 1. The contracts will be able to interoperate on the upper layers above RGB itself, but the client-side validation, the data structure, binary formats are immutable. So let me start with the progress updates. First of all, we have quite a big progress when large-scale changes in the core library. The reason for those changes was the fact that we were working on the secondary issuance and burn and replace procedures for RGB20, which are fungible tokens. Also, at the same time, we were using this opportunity because there is a lot of shared code to work on the implementation of non-fungible assets, and actually not a single type of non-fungible assets, but a set of types of non-fungible assets like suited for game industry digital art, for identity purposes, for reputation purposes, and for decentralized name management, and so on and so forth. There will be a separate presentation on this topic. I was planning to give it last time, but we hadn't time. It's also included in today's presentation, but I'm quite sure we wouldn't have time for that part. So probably one of the latest calls will be used on discussing the NFT progress. And because of that, because we were implementing this new functionality, which requires client-side validation, we used this opportunity to finalize the understanding how the API of the validation of any possible script extensions to RGB will be working. And while we haven't implemented all the functionality that we foresee as a part of RGB version 1, we have structured APIs, existing APIs, in a way that the stuff that I will be talking later, like virtual machine and specially designed languages, can be sticked in without modification of the client validated data binary structure. So we will be able to add this functionality later without breaking the protocol rules. And most of the talk I will be describing what is that functionality. Additionally to that, we have developed an API around to work with RGB20 assets, secondary issuance, and burn and replacement. This API will be used by the wallet, so we're providing a high-level data structures describing all the issues, history of burning operations, API for detecting how many assets are in circulation today, and so on and so forth. And the end result that I believe that over by the 10th of April, we will have this functionality exposed via user interfaces in the first sample applications like Bitcoin Pro for issuers and MyCitadel for token users. So it shall come with the next major update to these two into these two software packages. On the deeper level, we also have completed the functionality of what we call disclosures. Disclosures are the ways of sharing information about the smart contracts, RGB smart contracts, between different parties. And these disclosures are used for instance, for allocating change and paying change back to yourself, or when you need to do when you decide that you should comply with some regulations and need to expose the data not to the whole world, but to a specific party, you will be able to use this mechanism. We also designed a way how you can supply an arbitrary non-client validated data together with RGB smart contracts. That can be, for instance, a media resources linked to NFTs. It can be a song or a painting of arbitrary large size, and we will reutilize the existing infrastructure of Lightning Network with the Bifrost extensions to construct the querying and delivery system for this client-side validated data. No, sorry, not validated data. They are not validated by client-side validation. They are taken as large binary blobs of data, but this will help to build a broad range of decentralized applications, starting from content distribution, like music, videos, and so on, ownership rights management, and even somebody may try to design something like social networks, decentralized social networks, or decentralized GitHub with this facility, which will be operating on top of the Lightning Network, plus Bifrost protocol extensions, plus RGB smart contracts. So this is a very interesting avenue, and we will spend future calls, especially when we will be discussing Bifrost, to pay more attention into how this can be done. And we have done quite a few virtualization advancements, which I will be talking most of this presentation. Regarding the RGB20, which is fungible assets progress, we are completing the implementation of these procedures for secondary issuance and burn and replacement. And it actually led us to the need. So we are basically finalizing the RGB20 implementation with all this advanced functionality that we planned from the very beginning. And as a part of that finalization, we did, what we did is basically today RGB20 assets are shared via Genesis, which contains information only about the primary issue. To distribute information about the secondary issue, we need something else, because we can't do that as a part of Genesis. It can happen later. It requires different mechanism. And we decided to use the same mechanism as we are using for transfers, which is consignments. Consignments is data containers that have information about schema, Genesis, and arbitrary number of state transitions. So you can pack, related to a single smart contract. So you can pack all that information as consignment, and we are moving the distribution of the assets on the consignment-based distribution. Another thing that I haven't put into slides, but I need to reference that, is the fact that we did two things with the bulletproofs, which are the largest part of all history of operations. They occupy the largest part, and they are basically range proofs required to making sure that with all zero knowledge, no inflation happens underneath the scene. And previously, these bulletproofs were part of the commitments of client-validated committed data, so they can't be changed later. However, after some time ago, we found that, first of all, it's not required because we are committing to Pedersen commitments, and bulletproofs are not required to be committed to. And we designed a migration procedure when we are stopping committing to the bulletproofs, which will allow possible aggregation of historical bulletproofs. There are some limits, so this is still a research phase. We are not sure that it will be possible to aggregate all the information about bulletproofs, but certainly some optimizations for the size of the client-side validated data will be possible. And to unlock these future optimizations, we should remove the committing procedure to the bulletproofs values, which is safe, as we checked with Andrew Belstra, who is one of the creators of bulletproofs. So finally, we did that part of the story. So now with the new version of RGB core library, which will be 0.5. Together with all the advancements I will be talking today and I already described, this removal of the bulletproof commitments will also come to into play. The second part about the bulletproofs, that they were validated previously, they were validated with embedded procedures. I will explain what it is later. Right now, the validation of bulletproofs became a part of the schema. So basically, schema validates all bulletproofs if they are present, and you don't require the virtual machine, which we will be also talking later, to support that complex cryptography, which is a big news since implementation of the bulletproofs is a very tight bottleneck. And we finally implemented what we were calling subschema, where you can have a generic root schema for RGB20 assets, for instance. This is a large schema defining a lot of different forms of operations, very complex operations even. And subschema is basically a restricted version of the root schema, removing some unnecessary functionality, such that asset issuers can do something simpler than the generic case. And why this was required? Because in certain cases, it is impossible at the schema level to prohibit users from using certain functionality. Like we have a burn procedure and we have a burn and replace procedure, where the issuer is not only burning the assets, but reissues these assets once again. And this is quite risky operation in terms of that you have to introduce additional trust factor to the issuer. So you are not just trusting the issuer that he issues the proper supply, but also you trust the issuer he doesn't inflate that supply above the actually promised limit. While without this replacement procedure, you can verify that the issuer doesn't inflate supply. So sometimes it would be people will be interested in having contracts that prohibit burn and replacement procedure, so only burn operation is possible, and that can't be done at the genesis level. And you basically either can have both burn and replacement procedures or none of them. And with a subschema, it is possible to define a subschema which will allow only burn, but not burn and replacement. So we also did that subschema for those who would like to prevent and prove that as an issuer, they may burn some assets, but they have no right to reissue the asset. The reissuance is different from secondary issuance, because secondary issuance is limited by the genesis, where you promise how much assets can be in the future, while with a burn and replacement procedure, the reissuance happens that you are saying that I burned some assets and you can't prove that, so I reissue the asset once again. So these are different inflation mechanisms with a different trust models. So that's all for advancements, and now we can move to the main part of the presentation. But before that, probably I would like to check with the audience that there are no questions or things you'd like to discuss on that part.
Any questions, guys?
Giacomo, if you are here, if you have joined our call, there is one thing I would like to ask you to pay attention to and to check with that.
I'm here.
Yeah, hi. So basically, you remember our discussions about the introducing subschemas and that why they are required, why you can't do that without them. So I try to explain this part, but I'm not sure is it clear. So do you have any still considerations or concerns about this part of the RGB functionality?
Nothing specific. In general, I like the design of nested schemas, and I think that this discussion can be used to generalize two things that is not really the direction in which I think we're going here. But in principle, it could be used to generalize two things. One is, of course, as you said, for fungible tokens, different single tokens of the same, let's say, class. And then also for reissuance purposes, I think that like having like two contracts of the same kind of subschema could be could be a generalization of the reissue concept in a way. But I mean, I don't have any specific suggestion or criticism, just that in general, the nestificability of schemas is probably desirable in order to be able to express this kind of elastic hierarchy.
Right, thanks. I will just emphasize few security-related topics regarding subschemas, because introducing any additional complexity actually increases attack surface. So we paid quite a lot of attention into introducing subschemas in a way that they wouldn't produce additional significant security trade-offs. So first of all, we have only one level of hierarchy. There is a root schema and a subschemas, but you can't do subschema of subschema. So you are limited with the one level of hierarchy for now. The second is that subschemas can't extend functionality of the root schema. It can only restrict it. So it can be more restrictive than the main schema, but it can't introduce new types of operations or new types of state data or new types of metadata. It can only restrict the amount of the things that can be used. And later I will be showing the language that I think may be useful for defining the schemas, and there will be a special block where you define the schema, actually smart contract, as a restricted version of other smart contract, and the only content you can put there is the names of the fields and metadata and state types which you are removing from the schema. And the third is about scripting part, which we will be also discussing today. The root schema defines whether subschema can replace the implementation of the scripts or can't replace. So if root schema allows subschemas to change the scripting, then subschema can change the scripting code. If it doesn't allow at the root level, subschemas can't replace or do anything to scripts and has to conform to the same validation procedures as the root schema. So these are three main ways how we try to not introduce additional attack possibilities with subschema. All right. So probably I will move to the main part, which is virtualization of RGB validation.
Before we move, there is one question. Can you please remind the use cases for burn and replace procedures?
The main use case is, there are two main use cases. The first, the primary use case, is when you need to reduce the size of the history of the client validated data. This is the case for high velocity assets. Like if you have a USD tether, you may have millions of operations in the history, and then the amount of data you will be transferring with each operation will grow quite large. And the graph is very tightly connected, so basically you will store the most of the history of USD tether operations anyway on your local device. And for that, because from our analysis with Bitfinex, and we found that the graph is, while it's very well-connected graph, there are hubs in the history when the assets are passing through the exchange, for instance. And that at that point, an issuer can have a special interface with exchange, so he can basically burn this supply when it is in the exchange and reissue it once again. But basically this supply after issuance will have a zero history, like it will prune the history of the asset, which also adds a lot to confidentiality, plus it's a scalability factor, storage scalability factor. So that is the main reason. And actually, if you're not doing a high velocity asset, if you have, for instance, just the corporate shares, you don't need burn and replacement procedure, because it introduces additional required trust element to the issuer. And well, you wouldn't be able to get a large history. If you will even trade high frequency trade your shares, you will do that over the Lightning, which doesn't increase the history size. So that's why we did this subschema that prevents you from using burn and replace procedure. And the second reason for burn and replace procedure, that some issuers may like to replace those assets which were provably burned, but burned by occasion. For instance, somebody spent the transaction output without actually creating the client-side validated data. And that can be proven by a person who can, for instance, provide a extended public key and a derivation path from that extended public key used in the spending transaction. And that will prove that there is no commitment to any transfer operation and the assets were actually lost. So with these proofs, the issuer may also reissue that asset, taking that burnt output as an input for this reissuance operation. So again, this may be useful not only for USD Tether, but even for corporate shares. But again, it requires a level to trust because it's actually will be only the issuer who will be verifying this burn, the asset was burned indeed, and that's why the burn and reissue procedure may be required as well.
Okay, perfect. Thank you very much.
Any other questions?
Not for now, probably.
Okay, so I will continue. The next main part is actually a discussion of virtualization and scripting in RGB, and there was a lot of questions throughout the last week, and I decided just to make it part of the presentation instead of answering over and over again about the same things. So once and forever, I would like to set up the question about how RGB does client-side validation, what it is, how virtualization is used, virtual machines, scripts, languages, whatever. So I would like to define the terminology first. So with a client-side validation, what you actually validate? You validate two main things. The first, you validate internal data consistency and completeness, meaning that you have all the data required to see the actual state of the smart contract, and that these data are internally consistent. They are not self-contradictory. The second part of the client-side validation is the changes in the state, in the history of state inside the smart contract. Because like with Bitcoin transactions, you have a graph of historic operations which you validate. And it's quite clear that for the first part, internal data consistency and completeness, you don't need any form of scripting, virtual machine. You just check that you have all the data. It should be, and it is a part of RGB core library implementing the RGB standard. There is no place for scripting or any customization. It's not schema dependent. You just contract dependent. It's just generic for RGB. While with a state, it's a bit more complex because with a state, you have both conservative and dynamic part of validation, which I will be talking a bit later. But before that, I would like to pinpoint another important aspect is how RGB client-side validation is related to Bitcoin scripts and Bitcoin transaction validation. So all the state of RGB smart contracts is assigned to certain transaction outputs, well, Bitcoin transaction outputs, namely. And of course, when you need to modify that state, the only way you can do this operation is first by spending that output, and then by committing to a new state inside the transaction that spans that output. And it's quite obvious that in order to change the state, while you're required to spend the Bitcoin transaction output, you can do that only by providing a proper information to Bitcoin layer, and you will in fact utilize Bitcoin script to do the spending operation. So in this case, you can say that RGB reutilizes the security model of Bitcoin layer and actually uses the same Bitcoin scripting engine as used for the Bitcoins themselves, and we inheriting this privacy. What this Bitcoin scripting defines is the very precise thing: who can change the state, not how the state can be changed, but only who can change the state, who has the right to change the state, and that's what we are calling ownership. So Bitcoin script controls who owns, because only those who owns the keys from the specific transaction, Bitcoin transaction outputs, actually can change the state. So they own the state. However, that is not enough, because while you can have the right to change the state, you still need to change it. You have to define how you change the state. And of course, there could be invalid state changes and valid state changes. And you can differentiate on those changes at the level of Bitcoin script. In simple words, for instance, because Bitcoin transaction output doesn't contain amount of the asset, let's say we are talking about USDT. The USDT, the number of USDTs you have is not in Bitcoin transaction output. It's in the RGB client-side validated data. And while you have the rights to change, to move these assets by changing the Bitcoin transaction output, and you have all necessary keys, you may say that you had a 10 USD tethers, but will pay 20 USD tethers, which is invalid because you basically inflate the asset. So while the Bitcoin transaction level, you spend the output and everything is validated and correct, at the state and the client-side validated state, this is an incorrect operation. And you need some code that will actually validate, define, first of all, the rules of how the state can be changed, and then validate against that rules. So these are what we name RGB schema rules, which control how state may be changed to continue being valid. So Bitcoin script defines who can change the state, while RGB schema, and it's not script, I will explain why it's not script, controls how the state may change. So what is RGB schema? RGB schema is basically defines structure of client-side validated data. It's the first thing. So it defines which kind of state there might be exist. And when we are talking about kinds of state, what we are talking, in fact, is the forms of digital ownership rights. The ownership rights are controlled by Bitcoin script, but defined which forms of these rights can be there by the schema. What are these rights? Why they are different? Because even for some such simple things as RGB20 fungible assets, like USD Tether token, there are different forms of digital rights. There is, of course, there is a token ownership right, which means that you own some of these tokens. And if you own this, you have the right to transfer them. They are transferable and fungible. The second type of right is the issuance, secondary issuance right, which is completely different from the ownership of assets. And the same applies to to shares, corporate shares, for instance. So the right of issuance, it's another form of right, which is defined by RGB schema, and it has its own state. And if in case of asset ownership, the state data will actually define how much of the asset you own. For the case of inflation of the secondary issuance right, the state data will define how much of the asset you can issue. And you can do structure such things like if you have multiple departments globally, which can issue the additional supply to your asset, you can assign this right to different departments and distribute the total possible supply across those departments, limiting each of them how much they can issue. So this is all possible with RGB20. And this kind of functionality is actually not possible with Ethereum or other systems like that. So schema defines what rights exist in the client-side validated world. And also, of course, additional to rights, there are metadata and everything, all the ecosystem around this data. But additionally to the structure, the schema defines rules of how the state can change, what we just talked about on the previous slide. And these rules split into two categories. The first category is conservative rules. I call them conservative. It's my term. Maybe it's better to call them something else, but I haven't invented anything else than conservative. So what the conservative rules are basically relations between state types and rights. So the state type is actually amount of assets, and the right is the right to transfer the assets. And you establish relation between these two state types. And for instance, the amount of asset is stored as a zero knowledge Pedersen commitment with bulletproof data, while some other right, like the right to burn assets, have no state data. It's empty of state. We call that declarative state. And this different state for NFT assets, the state may be identify all the assets, which can't be stored as a Pedersen commitment, and instead has to be stored as a byte string, for instance. So these types of state and their relations to the UTXOs and the rights defined by the single-use seals is all defined by the schema and validated by the schema. And this type of schema evolution rights are conservative because you don't need scripting. You don't need anything. You can say that only those who can who have the right to do a secondary issuance can create a secondary issuance state transition, which may contain those and those data. And these rules are very well structured, and no script is required, and they are controlled by the core library. So we call them conservative. They are implemented once and used by all the possible schema. You define the future possible structure of the state transitions and how they can connect into a directed acyclic graph. The second part of the rules are dynamic rules, which are more complex, and in fact they define equations between the previous state data and the new state data. Like you have the sum of the assets in your outputs in the state transition must be exactly equal to the sum of input of the assets in your state transition, which is basically you are not producing inflation by moving the asset. And these rules are very custom to each specific type of the asset. You may have deflationary assets, inflationary by time, deflationary by transaction, paying fees to the issuer, and it's only fungible assets. If you talk about non-fungible, you can define even much more rules, and you can standardize that with a schema. You can create some data structure that will allow you to do whatever customization you need. And that's why this part we call dynamic, and this part actually requires some custom code to be embedded as a part of the schema and run by RGB client library in order to validate the smart contract. And basically this slide says the same, but in more broad way. And I'd like to say from here that only the client-side validation that applies only to two data structures, which are consignments and disclosures, and don't apply to the data containers. So what I'd like to emphasize is that RGB schema defining all those rules is not a script. It is a data structure. It is a data structure defining the rules for structuring data in RGB smart contract. However, the schema as a part of itself may contain script extensions and script components for the dynamic part of the validation, which I just described. So how it is implemented today? By today, I mean the version 0.4 and the version 0.5, which is currently in production and will be released in the next 2 weeks or so. Today, the schema is serialized as a binary strict encoded data. So it's basically a data structure that is serialized in some binary form. What is strict encoded? Strict encoded is a format for the binary encoding, which we had to create for the client-side validation world. So it's used everywhere in the RGB. It may be used in other client-side validation projects, which may happen one day. And it is used for serializing also schema, additional to many others. The schema is interpreted and verified, internally verified, or the RGB data is verified against the schema by RGB core library as a code in Rust, written in Rust. Basically, there is a verification part of the library which does all the verification. However, if the schema contains scripts, then a specific virtual machine or some embedded hard-coded procedures has to be used. And today, with the current version, we have only embedded procedures. We don't have a virtual machine. So embedded procedures are basically another procedures hard-coded into the core library. So we are hard-coding that the number of inputs must be equal to the number of outputs. We define this as a procedure, single procedure. And inside RGB20 schema, we say use embedded procedure with this ID, which matches the procedure that checks the equivalence between inputs and outputs. However, it's very restricted because nobody from outside RGB developers teams and those who has the push access to the RGB core library can extend the rules. For instance, you can't create inflationary asset with that. So we are looking into adding scripting support to the RGB. And later I will describe how it will be done. But first I will complete the topic of schema. So how the schema is looking like. The schema is looking like it's just a Rust code. You use the Rust code and you define the data structure inside the Rust code, which is called schema. And that's how it looks like. It's a part of the RGB20 schema. You define the genesis structure, metadata, types of owned rights, how much of them can be there, transitions, different forms of state transition. Here you have issuance. There are also transfer state transitions coming later. And here at the very bottom, you see the ABI, which says that there is a transition action. It's validate, the action that validates the transition data. And it uses embedded procedure referenced by some identifier, and that's all. You don't have script here. You just reference to hard-coded validation method. The same schema, because it's a binary data, so it's not the code, it's actually this data structure written with Rust, but you can write the same data structure with YAML or JSON or any other data format, XML probably. And here I just show how you can deserialize the same schema into a YAML format. And there are also, you can do that the same with the JSON and to debug the actual schema data. So you have a different form of the same schema representation. And for end users, the schema looks like this. It's a bag32 encoded string, which is actually the schema binary data. They are encoded using that strict encoding I told to talk about. Then they are zipped, compressed with a zip algorithm, but we are using special zip version, which is open source and standardized by RFC. So you don't require any license or anything like that. And on top of that, you encode this binary data. Why we zip encode? Because otherwise it will be lengthy and not very readable, meaning that there will be a lot of zeros inside of this, like which is not very useful. However, this is how it's done today. This is how the schema is defined today. But tomorrow, if we would like external developers doing their own types of schemas, new types of smart contracts, maybe social network, I don't know, you have to provide them with something more useful, like this YAML representation. You have the hard-coded identifiers as numbers. It's really hard to read and to write. And of course, you can't write this one. So what we are looking into is we drafted a concept of the possible language, which we called Contractum, for definition of RGB smart contracts. Basically, they define schema, but because each smart contract uses certain schema, we call that smart contract in general form. And here, how it can look like, I invite you to check this link on GitHub, Contractum Lang. It's very early days, and it will be released much later, even after the release of RGB version 1. The idea is that this language should not be like JavaScript or Solidity. Well, basically, it's modeled after the Rust, but should be much more readable. So non-developer should be able to read the sense out of the smart contract. And this is script language, because this is a data structured language like XML, HTML, YAML, and so on and so forth. It may contain scripts for dynamic validation, like here you have this validate procedure, which uses actually scripting. So the scripting is a part of Contractum language, but the Contractum language by itself is not a script language. And the languages also will be designed from a point of view that it will be impossible to define invalid or internally inconsistent schema. You can do that with a Rust code or with a YAML, for instance. You can define say that genesis may contain a metadata field, but you don't define the structure of that field for this specific type of for this specific identifier. But it will be impossible to do like something like that with this language. So this schema will be basically invalid. And of course, all the contracts issued under the schema will be invalid by the core library. But it's better to prevent that not at the runtime, but at compile time. And that's why we may need this language. Also, with this way of defining schema, you have a lot of repetition. So you declare the metadata fields, then you have to reference them. It's quite error-prone thing. And this is more a manageable, readable, auditable thing compared to the Rust-based schema definition. And for here, for instance, you see there is at the line 16, there is asset ownership. So the smart contract assigns asset ownership right, which can be multi, meaning that the value plus means that there can be one or more instances of this asset ownership. And there is a validate procedure for this ownership, which basically takes the difference between inputs and outputs. And if this difference is not exactly equal to 0, it creates an error saying that there is a conflation happening. So it's very readable. And this validate part is actually the scripting part of the language, while the rest is the data structure part. And I would like to pay some visualization of dynamic validation. Oh, sorry, no, not visualization. And the thing we are looking for is the virtualization of this dynamic scripted part of validation. Why we need this virtualization? It's not here yet, but why we will be working on that in the future? Because we need first distinguish dynamic and conservative parts of validation. It's a good coding practice. Second, we need to isolate the state of the contract from the logic of RGB core library. Like, you're doing the dynamic validation as as embedded procedure inside the core library, you have access to the rest of the library. It's a bad sandboxing practice. And the most important, that the virtualization may allow creation of custom schemata by in a permissionless way by external developers, meaning that the developers should not contain the RGB core library maintainers or LNPBP standards association. They can develop what they like and program the way they like without committing any pull request. So today it's not working like that. Today we don't have virtualization, and third parties cannot do a custom. While third parties can still do a custom schemata, this schemata may only use existing embedded procedures from RGB core library. So their functionality is very limited. And for instance, you can't do an inflationary asset or some non-standard type of schema operating off standard state. So today, the specific library for each schema exists, which we call by standard name, like RGB20 library for fungible assets. This library has an embedded schema in that binary, in that Rust form, like this. And this schema is passed to the Rust code of the RGB core library. And also the same schema references embedded procedures from the same RGB core library by identifiers. And when the end user provides some RGB consignment about the transfer operation, the core library validates this consignment against the schema using its own internal procedures and produce validation result. So that's how it works today. That's how it should be working. And we are looking to implement that with RGB version 2 standard. And this will be working that there will be independent smart contract developers, which are able to define their own smart contract schemas using Contractum code, as I showed. This Contractum code will be deterministically compiled into a valid schema. This valid schema will contain serialized bytecode for a virtual machine for a dynamic part of the validation. The issuer will use this compiled schema to issue an asset, and he will provide the binary schema, compiled binary schema, together with the issued asset to the core library. And when the asset owner will receive a transfer, he will get the consignment, call the core library together with the schema, because consignment will contain this schema. And the core library will be calling virtual machine on the dynamic part of the validation. And virtual machine will do the dynamic part validation in the sandboxed environment. How we plan to implement that? What is roadmap of supporting all of that? Well, basically, we are the first release of RGB version 1 code will not use virtual machine or this virtualization. It will continue utilizing embedded procedures. However, they are already with the current release in preparation, which is 0.5. We refactored all the API for the validation procedures in a way that you can plug in virtual machine into it without breaking the consensus on the client-side validated byte structure. So basically, the day when we have the virtual machine, when it will be released and you will have Contractum language and everything like that, you can compile the schema and it will be compatible with the current release of the library. So it wouldn't say that it's something invalid. It may say that you need to update the software to support, to include this new virtual machine, but it wouldn't say that the state is invalid. So it will be able to understand that the code, the schema uses specific virtual machine, and there is some bytecode which need to be run. So this is already part, but we don't have virtual machine yet. It is planned to be completed late this year or early next year. Sorry, I put the same year, but it's next year. And RGB core library will be updated with the virtual machine. It will be just basically the some release of the core library, and all wallets using it. Well, with the next version, they will supply this new release, and it will be quite seamless update, which we expect. Independently from that timeline, we will be also developing Contractum language. So that will simplify the development of the schema data and the scripts for dynamic part of the validation. And all of this does not affect wallet developers and those integrating existing RGB contracts into their software. It will affect only smart contract developers who will be creating new types of RGB smart contracts. So if you have a wallet supporting RGB20 assets, you shouldn't be worried about all of these updates, other than that at certain point you'll need to recompile your wallet with the new version of the library. So the final part of this talk today is actually what virtual machine shall we use for the RGB. But before that, again, I probably will make a small break to address possible questions and comments about the part which we just discussed.
So just you shared the link for Contractum. There is already work ongoing about that, or just the general idea? I didn't open the repository yet.
It's I wouldn't call it work. What I did is just I wrote how the language like that can look like to make sure that it is possible to create a readable, auditable Rust style language to define RGB smart contract the way the smart contract developer used to define smart contracts. And I found that it can be done. I was very satisfied with how it can look like. And I created a small extended BNF format definition of the language, which is formal definition of the language, a draft for that. So it's like a draft, very early stage. And I don't plan to work a lot on it right now. It will be worked later this year or beginning the next year, because again, with the current smart contracts, we have fungible assets, non-fungible assets. It will be when we will have much broader adoption of RGB, that when this language will be required, but not for the initial release. So it's an early draft or concept of how this language can look like and work. Maybe somebody will come with a better language, because there can be multiple languages. And if somebody sees it differently, you're free to play with that. Any other questions or comments?
I have organizational one. How many slides do you have? We're on our 48 minute of recording.
1, 2, 3, 4.
Okay, I think that can be enough.
Yeah. Any other questions? Yeah, the final part. Since we talked about plans to use virtualization, we need to define which virtual machine shall we use. And we received already, like, the first question, which is probably asked by the most of people being introduced with RGBs, what virtual machine are you using? Well, currently none, as I just explained. I just explained how it works without any virtual machine. But yes, we plan to use a virtual machine. And the plan was to use something with a simplicity. And we've been focused on completing many parts of RGB, and we hadn't enough time to plan that part in all details, because it was planned for the future anyway, and the simplicity wasn't ready. And when we completed the most of RGB, and the question arises again about the virtualization technology, we had to look into simplicity. And unfortunately, I wasn't satisfied with the probability of using simplicity, at least for RGB version 1, because of number of issues. First of all, simplicity is not a virtual machine. And for me, it's today, I have to say that I read the article about simplicity. There is only one source of truth about simplicity, which is an article. And this is article by a mathematician. And it is written as a scientific article. And well, I wrote it many times, read it many times, and I just don't understand what simplicity and how it works. And I'm being, well, developer working for all my life with IT industry. So at this stage, I doubt that normal developers will be able to understand what it is, because even for me, I don't know what simplicity is. It's certainly not a virtual machine. It says something about virtual machine, which they call bit virtual machine, which operates with bits. It's such a low level that it operates with the mathematical abstractions, basically. And the article defines not simplicity as a language, but more like mathematical formal model of constructing computations, which is very far from something that we can call a working language. And in terms of the implementation, it's not there yet. There are some libraries, but I wasn't able even to understand how they work internally or how they can be integrated. And this library seems to implement most of its functionality as an embedded procedures in the form that we're in RGB. So no reason of switching that, because simplicity is not yet ready to operate as a language or a virtual machine. Maybe it will use dialect of Haskell. It's not even defined at that stage. So for sure, we wouldn't be able to use it. But even if it will be completed in the next month or two, which I doubt, there is no tool chain for developers. There are only 2 people in the world who understand how it works and how it can be programmed. And it's too complex to understand even for me how to use it. So I think that while we are I'm really interested in the idea and values behind simplicity and the way they design it with a formal verification. But first of all, it will take years to be really used by the end user developers. And we have to postpone the plans to use simplicity for what we call RGB version 2, which will be in compatible protocol with the current version. Meaning that RGB should be able to support multiple virtual machines if we plan to add simplicity, which I think is a much better option for any other option. So since we don't have a simplicity for RGB version 2, and still want to do the virtualization, there is the question which virtual machine to use. Simplicity is not there. The real alternative to simplicity is WASM. And the same counter-arguments which are applied to WASM can be applied for other existing virtual machines on the market, which are, let's name them, LLVM, generic low-level open source virtual machine. So you can compare that to WASM, and they are actually cross-convertible. And proprietary virtual machines like GVM and Common Language Runtime by Microsoft, which much worse than WASM because it's first proprietary and designed for a customized environment, in fact, and don't run on the platforms like CLR. So, but even for WASM and LLVM, we have very negative things, because I tried to into WASM, and WASM itself is created for web browsers. It's not created for blockchain or even more restricted client-side validated operations. It was created to run inside the browser. So it has too many functionality, which is impossible to do in the blockchain application or client-side validated application. And that's why those projects who are using WASM as a part of their blockchains, like Polkadot, they have to work on their version of WASM, which is standard incompatible to the standard WASM. And it's been like the only version that exists on the market is done by Priority Labs doing the Polkadot, and these developers are being infamous of creating the systems. First of all, they developed EVM, and after that, they developed smart contracts, which were hacked multiple times using the EVM that they developed. And now they developed a non-standard compatible fork of WASM, which, like, I don't think that is a good idea to use it in RGB. So yeah, even if we will use WASM, we have to restructure the standard, re-implement the core of the library, and it's a huge work. And most of the WASM functionality is not required for RGB validation at all. So probably WASM is not a proper solution for RGB. What else is there? Well, there is some variants which are quite non-standards, like there is a ELE virtual machine and KeyVM. They are both created by IOHK, which does this Cardano project. For the Cardano project, what the interesting thing about them is that they are done with a formal verification. So basically, they are done also by mathematicians, and KeyVM is the version of EVM, which is re-implemented with a formal mathematics, and ELE is more advanced version of the same KeyVM. So shall we use them? Well, it's basically the same old way EVM, which we are not really looking into being compatible with, because even if we will have EVM, the logic of client-side validated contracts is so different from the Ethereum contracts that you can't migrate them, even if you are bytecode compatible. You can't migrate the contracts. And we would like the most of all, we would like to prevent developers of writing smart contracts using simplicity. And if we will use ELE or KVM, they will be able to do that, which is really bad practice. And it has, again, a lot of custom unneeded functionality. It's created for non-Bitcoin type, UTXO type blockchain, so it's basically incompatible. So I don't think that there is any single reason of using ELE or KVM. What options are there? Well, none. So the original idea of using something custom seemed really bad, because again, another thing to develop, but it seems that we have either to wait to simplicity or do something custom, because nothing is there. And again, as I said, the plan of implementing virtualization will happen after the release of RGB version 1, so the virtual machine will be added later. So we are not in rush in doing that. And we may do something that is actually required for the client-side validation work. And what is required for client-side validation work is very different from the requirements for all existing virtual machines. And this set of requirements I defined as our future hypothetical virtual machine called AluVM, probably to pronounce it, but this is abbreviation coming from Magnetic Logic Unit. Why this abbreviation? Because basically this virtual machine is not that sort of virtual machines like GVM. It implements its arithmetical processor, doing nothing other than arithmetics. And it's purely functional in both computer science and mathematical way. So basically, all operations is a function on inputs producing some deterministic output. And these operations are arithmetical. Even though it will support elliptic curve arithmetics, it's still arithmetics, like addition and others. And it has no external state. It just converts a set of inputs into false or true validation results. Because of that, it's extremely robust, because, first of all, there are no functional state machines in the market today, defining the virtual machine as a state machine and functional state machine. It's very deterministic. It will be very deterministic if designed according to this criteria. There will be no exceptions of the virtual machine itself. It will use no stack. It will be register-based, and again, it's very different. All of the existing virtual machines, they are stack-based. It will have no random memory access, no input-output operations, no memory allocation operations. So the most of the reasons for the undeterminism and instability are removed from the virtual machine. And it doesn't need to be, because the only thing it should do is to validate client-side validated data, validating data which are sandboxed. And it doesn't need to have a random memory access. While, for instance, VASM has to do, which makes the language not the language, but the standard much more complex and less robust. If the code compiles into AluVM bytecode, it will always run successfully without an exception. And it will be, because of these criteria, it will be very easy to implement it in hardware like FPGAs, because first of all, it will be RISC-based, so very limited, restricted set of arithmetic operations, registry-based, which is again suited for hardware, and purely functional and exceptionless. The original prototype of how it can be done is by this GitHub link. So all those who are interested in contributing to this future developments, we are not, again, we'll be focusing on that now. We were just making sure that after the release of RGB core library for mainnet, we will be able to do this virtual machine without breaking client-side virtualization compatibility. So all APIs and bytecode structures are accounts for the possibility of use of the virtual machine, which is functional virtual machine or something like simplicity-based virtual machine. So that's all what we did for the current version of RGB in this regard. And the development of the virtual machine will go in parallel, initially at very low rate. To complete this part is basically I did selection criteria between doing living with the status quo or working on this new type of AluVM, or waiting for simplicity, or using the unready simplicity today, or using VASM. I already did a presentation on this slide last call. I wouldn't be going through all the details. You will be able to check it later. We will share the presentation. Basically, I put each of these criteria into 3 categories, like security, implementation complexity, and extensibility. Put a number for each of the choices. And I got the overall rating, meaning that it's better to have embedded procedures than going with the simplicity while it's not ready, because while it's extremely secure, much ahead of any other options, you have no way of implementing it or extending it today. And VASM is worse than having embedded procedures. So the only way forward in the next year will be, or 2, will be implementing AluVM and adding that as a component to the RGB core library. That's all. Questions and comments? Am I still online?
Yes, you are. Okay.
Okay, I think we can finalize the call then.
Sure. Thank you for the presentation, Maxim. Guys, if you have any questions, feel free to drop them to the Common RGB chat, and all the information will be uploaded as usual. And thank you for being with us today. Bye-bye.
Bye-bye.